our closed system that we were talking about. And same thing affects in boiling too. What two factors affect evaporation? Number one is temperature. What's the second thing that affects evaporation? Huh? Very good. That is most excellent. Okay, temperature and surface area. Okay, temperature and surface area are correct. Any questions? I'm going to cheat something so she can come observe again.
I got it. I got this. You hear working hard.
All right, so what affects the rate of condensation? Now, there's only one thing that affects the rate in which the gas up here condenses. Now, you cannot give me one of those two answers. Those two answers affect the rate at which it evaporates. So, you cannot give me one of those answers for the rate at which it condenses. So, can anybody give me something that you think affects the rate at which it will then turn back into a liquid?
Humidity.
All right. What makes up humidity?
The moisture in the air.
Okay, the moisture in the air. You're on the right track with that. What'd y'all say over there? Put that thing on vibrate. All right. I need something more than just saying humidity or moisture in the air. The what? All right, what about the vapor?
The amount of it.
The amount of the vapor. Now, the amount of the vapor has a new vocabulary word. The amount of the vapor is called concentration. Okay? The amount of vapor is a new vocabulary word for us called concentration. Okay? Concentration is essentially the number of particles per volume. So when you said humidity, that's just more water per volume. So when there's more water in the air, it's more humid. When there's less water in the air, it's less humid. Okay? So condensation means there's more vapor. If you have a higher concentration of vapor, you're going to condense more. If there's a smaller concentration of vapor, you're not going to condense as much. So right now, looking outside, you would tell me, is there a higher or lower concentration of water in the air? There's a higher concentration of water in the air because it looks like it's going to do what at any minute? Rain. At least you got that phone. Now, yesterday when you looked outside, how did it look?
Sunny.
Looked pretty sunny. So what'd you tell me about the concentration of water vapor outside? It was pretty low. Okay? Questions about those two? All right. So 3 and 4 we did yesterday, so we should be able to answer. All right. So number 3. What happens to the evaporation and the amount of water in a liquid if temperature is raised inside a closed system? So what happens to evaporation if we raise temperature, Salma? What happens to our evaporation if we raise the temperature? Does it go up or down? It goes up. All right. What happens to our amount of water if we raise the temperature? Rebecca? That's right. Everybody okay with that? Okay. Why does our water decrease? Our water decreases because it turns into what?
Water.
It turns into water vapor or gas. All right. Number 4. If we lower the temperature this time, okay, we're lowering the temperature. What happens to our amount of water this time, Bryce? If we lower the temperature, what happens to our amount of water? It increases. More of it becomes water. All right. What happens to our amount of vapor if we lower the temperature, Alicia? We get more vapor or less vapor? You get less vapor because it stays as water. Everybody okay with that? Yes or no?
Yes.
Okay. Everybody feel okay with what we did yesterday? All right. I don't guess I need to change. I need to stay on the same slide. All right. So let's go back to boiling because we need to learn how to read a graph. All right, before I do, if we go back to where we were yesterday real quick. What do we call that? Pressure, right there above the pot. Who remembers?
Cooler.
We call it what? All right, there'll be cool air above it, but what do we call that pressure directly above the pot exerted by those particles? You have fun.
Equal vapor.
Say what? What did you say, Betsy Bay?
Equal amount of vapor.
That's called equilibrium. Equilibrium vapor pressure. Okay? Every liquid that boils, everybody in here at some point, whether you use a microwave or a stove, has boiled water. Maybe you like to camp and you've done it outside on a camp stove. As long as it's not like camp, my idea of camp is all in. All right? At some point, I don't like bugs, I don't like the outside. All right? If you heated water, brought it to a boil, you have had bubbles, right? If you put your hand over the pot without burning yourself, how does your hand feel if you pull it away?
Wet.
Wet. That wet is the vapor, the gas. All right? That gas creates the pressure. That pressure is called equilibrium vapor pressure. All right? If I ask you on the test, when does water boil? What do you tell me? Can virtually guarantee y'all are going to give me the wrong answer. When does water boil?
When it's heated.
Okay, that's still the wrong answer. Thank you, dear.
Hold on.
When does water boil?
When the bubbles start.
Okay, it's not the right answer. When do you see the bubbles?
When you apply heat.
No.
So it's how much pressure is the.
There we go. Now. The only thing you said wrong is it's not atomic pressure, it's what kind of pressure? There you go. When atmospheric pressure equals equilibrium vapor pressure. Okay? This pressure above the pot, does it start at a particular pressure? No. Betsy Bay goes home, had a rough workout. She's hungry. She decides, I'm going to make me some oodles and noodles. I got to boil my water because she's lazy, it's cheap, fast. Only takes 3 minutes to cook noodles and noodles. Got to boil some water. Inside of 10 minutes, she can be eating some dinner. Okay? Mom's not got time to fix her some food tonight when she gets home. 10 minutes, she can have dinner. So she puts some water on the stove and she heats it up. Now, as soon as she turns the stove on, it gets hot. Heats the bottom of the pan. The heat transfers to the water. The water starts moving faster. Is it automatically going to boil?
No.
No, it's not. So, as the water starts to heat, it moves faster. Some of it begins to evaporate. Some particles are going to begin to form up here. There's going to begin to be a pressure. Is it going to automatically be atmospheric pressure initially? No. As it continues to heat, more evaporates. Is it going to be atmospheric pressure then? No. As it continues to heat, more particles come up here. All right? It hits that cool air Bryce was talking about. Some of it condenses. More of it heats. The whole time it's heating, what's happening to this pressure? The whole time it's heating. Is the pressure increasing or is it decreasing? It's increasing. As long as that pot's heating up, that pressure is increasing. The whole time it's heating, it keeps getting higher and higher. As long as that pressure continues to increase, it's getting closer to what? To atmospheric pressure. As long as it keeps heating, it's getting there. It's getting there. When you start to see those what, Selma? Bubbles, we know we're getting closer. When we start to see those big bubbles pop up from the bottom, what do we know has happened? It's boiling. We have hit what?
That
we've hit atmospheric pressure. Atmospheric pressure is the pressure that's in the what? In the room, in your house, outside in the air. It's the pressure that pushes on our lungs. Take a deep breath. You feel that pushes on your lungs? That's atmospheric pressure. That pressure is pushing on that water in the pot. That pot that boils is pushing up on the atmosphere. Those two things have to be equal for those big bubbles to come off the bottom. Until those two pressures are equal, you don't see those big bubbles. Okay? Now, is atmospheric pressure always the same? Think earth science. When the big sun is out, what kind of pressure do we have? High or low? Did y'all have earth science?
When the what?
When the sun is out. Y'all didn't learn high pressure when the big sun's out. Rainy meant low pressure.
No.
Usually everybody learns that.
Not me.
Y'all want to teach high pressure, sun's out, low pressure, it's rainy and cloudy?
Yes.
Yes, that's what I thought. Everybody learns that in earth science.
Yes.
They're all looking at me like I'm crazy.
I didn't learn it.
I think I had to give you the.
No, I wasn't.
Okay, so today it's rainy and cloudy outside. It's low pressure. All right, when it's sunny and nice outside, it's a high pressure day. So if it's high pressure outside and low pressure, is atmospheric pressure going to be the same? That's my point. No. So is water going to boil the same on a rainy day and on a sunny day?
No.
No. Okay? So today is a low pressure day. Is the boiling point going to be the same on a low pressure day? No. So it's lower pressure, it's going to boil faster today. Okay? If it's a sunny day when Betsy Bay makes her oodles and noodles, it's going to boil faster. Or sorry, slower, because it's going to be a higher temperature. Okay? Now, yesterday when we did this, we drew some mountains, we drew some Piedmont, we drew some coast. Where did we say the high pressure was at? The coast. So if we have high pressure down here and low pressure up here, where did we say the highest boiling point would be? Where? Where do we say the high pressure was? Down here. So where's the high boiling point going to be?
In the cold.
At the coast. Wherever the high pressure is, that's where the high boiling point is. Okay? Wherever the low pressure is, that's where the what is? The low boiling point. Now, how does that affect cook times? Where do you cook faster?
Coast.
At the coast. Why are you going to cook faster at the coast?
Because you're lower elevation.
You cook faster because you have a what? You have a higher temperature. Okay? You cook slower up here because you have a lower temperature. It's a lower boiling point. Just like if you went home and you wanted to cook something. All right? If you cook it at a higher temperature, it does what? It cooks faster. Have y'all ever baked anything or cooked anything? Or y'all just wait on other people to cook for you? You cook some for yourself?
But on high.
You cook on high. So if you cook on high, it does what?
It cooks faster.
It cooks faster. So that's why foods cook faster at the coast than they do in the mountains. So right now, if I sent y'all all to the grocery store, and I said go buy a Betty Crocker or a Duncan Hines cake box, okay? If you read the side of the cake box, it's going to say at elevations of over 3,500 feet. It's going to say cook 10 minutes longer. Why does it say cook 10 minutes longer at elevations of over 3,500 feet? It cooks at a lower temperature. So you got to cook it longer because it cooks at a lower temperature. Okay? It cooks faster down here because it cooks at a higher temperature because there's more pressure down here. Okay? It makes a difference. Y'all, does that make sense to the 9 people I'm talking to?
Yes.
Are y'all sure?
Yes.
All right. I'm trying to review to make sure everybody's with me here. All right. So let's talk about a graph now that I feel like I've reviewed yesterday and most of y'all are nodding at me like, I'm with you, Miss Wall. Now, reading an equilibrium vapor pressure graph is reading a graph like in math class, just like you've always read a graph. The only difference is one tiny little thing. Now, reading this graph has pressure over here on Y and temperature on X. And it's usually going to have a curve in it. Now, the graph we are going to read has 3 graphs on it, and I gave it to you the other day. It's on the back side. Now, if I ask you to read temperature and you have a pressure, all right, so if I know the pressure, let's just say the pressure is 400 torr, and I want to know the temperature. Okay? If I know the pressure is 400 torr, can we all agree that I just read over to the graph and then I do what? Read down. Everybody's okay with that, right? And if I knew, let's just say that the temperature was 50 degrees Celsius, I would read up to the graph and I'd read over, right? Everybody would be okay with that, right?
Yeah.
All right. The only thing we have to add to this is something we're going to learn when we get down here to this phase diagram. All right? And it's called normal boiling point. Okay? And the key word is normal. And you're going to hear this again when we do a phase diagram. All right? The word normal means at standard pressure. So, do you remember what standard pressures were? What were they? 1 ATM. What else could you have?
273.
All right, no, that's a temperature. Give me another pressure.
760.
760. Give me a unit that went with it. Torr. All right. Another one.
760
Of mercury.
All right. And give me one more.
1.012.
All right. 101.325. What's the unit for it? KPA. Now, you won't see PA on this one because that times 10 to the 5th really makes it difficult to do on a graph. So you're not going to see PA. You will see one of those 4 units as your graph unit on the y-axis, but you're not going to see PA. Okay? So all you have to do is draw a line across the graph at standard pressure the boiling point is the intersection with the graph. Okay, we're going to label it on our graph we just drew. All right, you're just going to draw that line in, and then it will be the intersection with the graph. Wherever that happens to fall. All right, everybody there? Do I need to wait? See a couple still writing. All right, we there? Salma, you got it? You need me to wait? Okay. All right, so if we go back to my graph, all right, what did I label my x-axis in?
Tor.
Tor, or y-axis, sorry, tor. All right, so if I look at my y-axis, I labeled it in tor. So you would have to find standard pressure in tor. So what is the number for standard pressure in tor? 760, okay? So you're going to find 760. So let's just say 760 is here, okay? Now, I told you to draw in a line, so I just draw my graph, all right? So draw a line in on your graph. Now, you're looking for the intersection of that line with your graph, right? So, where is the intersection of that line and your graph? Right here is the intersection, okay? That is the intersection. So that is the normal boiling point. Okay? So, how do you find the temperature that is that normal boiling point? You just read down. So, read all the way down to find that temperature. We'll say that it's 75 degrees Celsius. I'll just make up a number. Okay? You're going to do this with real numbers in a second. Okay? Everybody got it? All right. Now, the other day, I gave you a graph that had a staircase on it, and it had a backside. Does everybody have what they need off this? Because I'm going to minimize it and pull up the other graph. And I told you not to lose that backside because I put it on the back to save some space. So see if you can find it.
Good, because that's what I just answered. Phase and pressure.
Probably get out of my boots. Oh my God. If it's somebody's law, I don't know who's on your. Of course, I just helped resource officer on exam questions. I'm like, I know this is kind of what they say, right? There's no reason. Just read it.
He still does something. I know.
No. All right, so on the back side. Okay, let me see if I can find an extra. Anybody else down here that ever did this? All right, so in the first three, you're finding what was the pressure, I think. Or you find the temperature? No, actually, find the temperature of those. The next three, you're finding the pressure. And then the next three, you're finding the normal boiling point. Okay? So see if you can do those. And I wanted to help those of you who are stuck. Grab a pencil. All right, who's got a question? And remember, you're gonna be estimating here. They're not all gonna be exact answers. We're just gonna be in the ballpark. So don't feel like you're wrong if you're not exactly what everybody else has. No, look, okay. Yeah. All right, anybody got a question yet? I know y'all gotta have something. I know there's only 9 of us. So what now?
Would you put receipt?
How we decide?
I mean, what?
What do you think?
Miss Wall, can you compare, please? And
Mhm.
what we have before? Which one has like,
Think about it. We'll talk about it in a second.
is it the fresh one? Because I got 35 with this one already, so this is my 400.
And that's what you estimate.
Yeah. Do we put a date behind it or something?
Yeah. Hey, what's your Rebecca? You okay? Okay. Jennifer, how about you? That's reason that number 10, by the way, that is correct. That's a good reason that number 10, that is correct. When does AP testing stop? So we do our benchmark. Anybody here take government and politics?
I do,
You do,
yes.
and that is,
They moved it, they had ordered the wrong test, so now it's on 17.
okay. 17th is when?
Next Wednesday. It's next Tuesday.
Is next Tuesday.
It's next Tuesday.
And then the 12th is when?
Friday.
12th is Friday.
Friday.
Anybody taking that AP test?
What is it? Oh, you been Geo?
That doesn't matter. That's next week. Anybody taking one Friday? I'm trying to avoid giving our benchmark on an AP test day. I don't care if people are just absent. I'm just trying to avoid AP tests. Anybody in this class in human geography? Anybody know?
Yeah.
It wouldn't be on our list if we didn't offer.
Myers teaches it.
Really?
'Cause that would be Friday.
So for number 7, what is number 1 and 4? Do I use 760?
Mhm. Yep. You do. Are we just waiting on Betts Bay and Salma
And Bryce.
and Bryce? All right, finish it up. Mhm.
Use what is 760?
This is a normal one? Oh,
How
yeah.
do you do many?
Scary.
How do you do many? I never had any interest in that.
Really?
Yep, I don't know how it works.
What other things can you teach other than translating science?
I think technically I can teach physics, and I'm certified to teach half my course load of math.
Okay, what can you teach? It's another field of courses.
Which liquid has the strongest?
You know, which one?
Damn, you don't know that already? Yeah, I got it.
Huh?
Yeah, that's the easiest one. Let's see this.
Probably.
Okay, I'm done.
Do, what's that password they called that you emailed me about? It's
What is
called
it?
NC Education password.
I'm always.
All right, so in the first one, it said, let me find mine so I have some idea what the questions are. So I don't have to ask you what every question says. All right, so the first one says 400 tour. All right, so 400 tour, let's see if Miss Wall can draw a straight line today. Not terrible. All right, so from there, if we read down, see if I can manage it twice. Not terrible. Not fabulous, but not terrible. All right, what'd you come up with in number 1, Salma?
35.
Okay. Got 35, what'd you come up with? 37, what'd you come up with, Bryce?
37.
Okay, so I got 35, 37, 37. I got 36. All right, everybody in that range, number 1? All right, what'd you get for number 2, Alicia? I got 70, what'd you get?
69.
69, what'd you get, Eric?
69.
All right, everybody good with that? Mine looks about 68-ish up there, but that's close enough, given I'm working on the smart board. All right, number 3, what'd you get, Juliana? 95, what'd you get, Sarah Ellie? You got 100, what'd you get, Betsy Bay?
98.
98, and I got 97. Looks about that on the board. Everybody good with those? All right, so if I get rid of those, the next one had what temperature? 35. All right, let's see if I can do
Oh
35.
my God.
All right, so about halfway. Ooh, that's a little squiggly. Let's try that again. That's not terrible. All right, so
It's gonna be under.
How much I come
all right, so what did you come up with for number 4? What'd you put there, Bryce? You got 350. What'd you put for number 4, Alicia? 400. So we got 350. We got 400. What'd you put, Juliana? 400. I actually had 370. All right, so somewhere between 350 and 400. Are we good on number 4? All right, for number 5, what'd you put there, Eric? 180. That's actually what I have. What do you have, Salma? 200. What'd you have, Rebecca? 200. All right, number 6. What'd you put there, Jennifer? 50. What'd you put, Betsy Bay?
50.
What'd you put, Sarah Ellie? Well, that's 4 of us that agree. All right, number 7. All right, we drew in a line where, Alicia? 760. So we're estimating here where 760 falls. So we're already going to have a little bit of disagreement in estimating to begin with. So we're going to have a little more play in these answers. Those lines look terrible. Those aren't even straight. All right, what'd you come up with in number 7, Rebecca? 52? What'd you come up with, Salma?
51.
51. What'd you come up with, Eric?
For which one?
Number 7.
Number 7, I have 55.
All right, so I had 52 too. So we got 51, 52, and a 55. Are we in that range? All right, number 8. What do you have, Juliana? I got 80. Bryce, what you got? 80. What you got, Jennifer?
80.
All right, I got 81. All right, and number 9. What do you have, Betsy Bay? 108. What you got, Alicia? 110. And what you got, Sarah Ellie? 108. I had 110. All right, and the last one. Which liquid has the strongest intermolecular forces? What'd you pick, Rebecca?
What does that mean?
You don't know. All right, anybody know other than Jennifer?
I picked C.
All right, why'd you pick C?
Because it was kind of higher pulling.
That's exactly right. Okay, C has the highest boiling point. Now, when we say intermolecular forces, all right, does anybody know what intermolecular forces I'm referring to?
No, man.
Dipole, hydrogen bonding, and London dispersion forces. All right, they would be the highest because they have the highest boiling point. Highest boiling point means strongest bond, and it also means it's the hardest to break. All right, that goes back to our bonding unit that we've already studied this semester. That's review information. Okay, that's information y'all are supposed to carry from unit to unit. All right, that's tying in from the last unit before the gas laws. Okay, but C, because it has the highest boiling point. Okay, questions? Yes, sir. Mm-hmm. All right, does everybody have what they need? Can I turn? Okay, now we're going to talk about phase diagram. A phase diagram is just a graph, all right, and we need to learn to read the parts of the graph. Instead of giving you one that's already drawn, I'm going to freehand as we go. I like doing it better last semester that way, so we're going to keep doing it that way. I'm going to put my pen. All right. Okay, a phase diagram shows the temperature and pressure at which a solid, liquid, and gas can exist. Now, there are various points on this graph that you're going to have to be able to find. Now, we're going to draw and label these points on the graph. I'm going to draw a very small one to label certain points, and then I'm going to draw a bigger one to label other points. First of all, I'm just drawing the small one first. Temperature and pressure are always in the same spot, just like it was with the equilibrium vapor graph, so that makes it nice and easy. It always is in a Y shape. Okay, it's always in a Y shape. Now, in the Y shape, the solid is always here. The liquid is always in the middle of the Y, and the gas is always below the Y. That never changes. Okay? Everything else about the phase diagram I will draw on the next board in a larger graph because I need to be able to write on the graph. But those are the easiest parts to keep straight about the phase diagram. It's always in a Y shape. The liquid is always in the center of the Y. The solid is to the left, and the gas is below the Y shape. Sometimes it's less Y looking, sometimes it's more Y looking. But a phase diagram always has that general shape. Now, we have to learn to find the triple point, the critical point, and the normal melting and boiling point. Is everybody caught up? Okay. Now, all right, so I'm going to draw it larger. Temperature, pressure, and I'm just going to write S, L, and G this time. Now, the first thing I want to tell you about it, first of all, these lines, all right, represent equilibrium. Okay, those lines represent equilibrium. Now, the question is, what do they represent equilibrium for? Well, it depends on what they're between. This line represents equilibrium between what? This is a solid, and that's a what? So this would be equilibrium between, what's the state change that took place from a solid to a gas? What do we call it? Think back a couple days. Oh my God, you're killing me. Sublimation. And what's the opposite to go from a gas to a solid? This is why y'all struggle on the quizzes. Now, you notice how I haven't assigned homework the last couple days? What was the homework? So when you come back, what are you supposed to be able to tell me? This. So what is the opposite of sublimation? Deposition. All right, so this here would be equilibrium between evaporation and what? Condensation. And this would be equilibrium between what two things? Solid to liquid, liquid to solid. Melting and freezing. Okay, so each of those lines represents equilibrium. All right, this one would be solid to gas. So this would be sublimation to deposition. Sublimation would be solid to gas. Gas to solid would be deposition. Solid to liquid is melting. Liquid back into solid is freezing. Liquid to gas is evaporation. Gas back into liquid is condensation. Okay? Are you with me on that? Yes or no? Can you tell me who gives off heat and who absorbs heat? Some of you that probably can. Some of you can't. If you can't, you need to study. All right. The first point you have to be able to find is called the triple point. The triple point is the point at which a solid, liquid, and gas all exist at equilibrium. Okay, it's the point at which a solid, a liquid, and a gas all exist at equilibrium. Now, to find this is the easiest one to find. Nobody ever gets this wrong on the test if they study and practice. It's the point that the solid liquid and the liquid vapor line intersect. Okay? So picture the solid liquid line, okay, solid liquid, and the vapor line intersect right there. Everybody there? All right, so if we go back to our graph, this point right here, that's the solid liquid line. Everybody see it? This is the liquid vapor line. Here, I'll even change that to vapor since I keep calling it vapor. All right, right there. That is called the triple point. Everybody with me? That's easy to find, right? It's the easiest one on there to find. Critical point's pretty easy too. Oops, that raised part of my x-axis. Everybody there?
Yes.
Okay. Now, the critical point is kind of odd. Because, and I don't know why scientists did this, instead of making the critical point one definition like the triple point, they split it up. They made it the critical temperature, and they made it a separate definition, and then they made the critical pressure a separate definition. Instead of just making it one definition like the triple point, one definition, don't ask me why, I have no idea. All right, the critical temperature is the temperature above which a liquid can no longer exist. All right. And the critical pressure is defined slightly different. It's defined as the lowest pressure at the critical temperature at which a liquid can still exist. Why scientists did this again? I have no idea, so don't ask me. All right. But basically, Once you pass this point, once you pass the critical point, a liquid is no longer there. You're now what state? Once you pass this point, you're no longer a liquid, you're a what? You're a what? You're a gas. So, how are we going to find this on the graph? If you know that we're no longer a liquid, we're a gas. How are we going to find it? Where's it going to be? It's going to be on the liquid vapor line. That's right. It's on the liquid vapor line, and it is usually at the end. Okay? Sometimes there is a dot. Okay? If there's no dot, it's just the end. Okay? It's nice when there's a dot because it's easy to recognize that way. But sometimes they just don't draw a dot, so it's just the end of the liquid vapor line. Who am I waiting on? All right, got it? All right, so if I go back, so did I draw a dot on mine? No.
Ms. Wall,
Yes.
I see Juliana Valdez in guidance, please.
Sure.
Excuse me?
Yes, ma'am.
Thank you.
Welcome. So we got 9 people here. Take another one. All right, so when you look at that line, I put a dot there this time. So when I put that dot there, this is my critical point. Okay? Right there at the end. But if there's not a dot, that's where it would be. Now, the last 2 things we have to find are those normal boiling and melting points. All right, everybody there? Got it? Got it. All right, so what, let me change colors again. What did we say about the word normal just a minute ago? All right, it had to be at standard, not temperature, at standard pressure. Okay? Now, because I said melting point, what line is this going to have to be on? It's at standard pressure, but is it going to be the solid liquid or the liquid vapor? All right, so it's at standard pressure on the solid liquid line.
How do you know which one?
How do you know which one what?
How do you know what line to choose?
Because it says melting. Or if it's, let me put this, freezing. Okay, it'll be the solid liquid because melting means you change from a solid into a liquid, and freezing means you go from a liquid into a solid. Now, the opposite of that is the normal boiling point. So, because I use the word normal again, it has to be at standard pressure. Now, which line is this one going to be on if I say boiling? Where does boiling take place? The gas what? Yes. So that one has to be on the liquid vapor line. Okay? Has to be on the liquid vapor line. Okay, so if we go back to our graph, all right, let's put our unit in ATMs this time. All right, we did it in torr last time. All right, what is standard pressure in atmospheres? All right, everybody with us on one? Jennifer, get off that phone. I'd like to be on my phone reading my book too, but I'm not. All right, so we got ATMs. That's they said standard pressure is 1. All right, so what I tell you to do with standard pressure, draw what across the graph? A line. Bryce, wake up. I might be laying home on my couch taking a nap too, but I can't do that either. Okay, so I drew a line across my graph. All right, so once I draw my graph, I'm looking for the what? The intersections, right? So the intersection that's right here is which line? Salma, which line is this that I drew a dot on? The solid to liquid. So what is that point? If it's the solid to liquid line, am I melting or am I boiling? What? Melting. So that's my normal melting point. Okay. So this point over here, change it. That's changing from a what to a what, Alicia? That's changing from a what to a what? So that's my normal boiling point. Good. Yes, always going to be paper down there. It's never going to change. Only for you and Bryce. All right, I want you to answer these 11 questions. See what we can do. There's one for Brian. That's one for Brian. Take home. All right, so find me an answer to those 11. This is the substance. So it's must be one test. All right, so this whole thing is the substance. So it's just asking what is the substance's normal melting point. So, right. So when you look there, you just look here and then you read that and you say it's. Yep. That's all you gotta do. Yep, that's it. Anybody else got a question? All right, so where's the normal melting point on the graph? All right, so you're going to read down and you're going to get that. Yep. we just finished normal melting point, normal boiling point. So if you want, go up to the blue arrows and click over to get the notes, Juliana, and then we're answering those questions in practice. All right, at what temperature is it impossible to liquefy the substance no matter what the pressure? Was that triple, critical, or normal melting boiling point? Mhm. That would be the definition for critical point. So where's the critical point on the graph?
Right here.
Yep, so what's the, no matter what the temperature, so what temperature goes with that? Yep, that's what's right there. There you go. You found it.
What about that?
It's true.
So do you put B or the triple? You said what?
Can you do what? Yeah. Sorry, I wouldn't listen, or I couldn't hear you.
Number 10 is the density of the solid right here. Then the resting.
Mm-hmm.
Is that talking about, like, why is it bigger?
Yep, it's just asking you if it's more or less.
Okay.
All right, how many of us need more time? Anybody? Or are we in good shape? No, Juliana's now got her notes, so anybody need more time?
10 and 11.
You what?
10 and 11.
You need help with 10 and 11? Okay. All right, so can I take this down and pull the graph up? Yeah? All right. If this is the one I want, or it's a different one. All right, that's the one I want right there. All right, so find mine. Question 1. What section represents the solid? A. What section represents the liquid? And the gas or vapor? All right, what's the triple point? And what's the critical point? Everybody okay with those? Okay, so what's the substance's normal melting point? 60. Everybody okay with that? So you're going to find standard pressure, which is here, right? The line's already drawn in for you. So you're looking for the intersection, which is here. You read down, and it's 60. Everybody okay with that? Normal boiling point, same thing. The line's already drawn in. Find the intersection, read down, is 100. All right. At what temperature is it impossible to liquefy the substance no matter the pressure? What is that the definition of? that we talked about today? The critical point, and the critical point is E, right? So what temperature does that go with? 110. Everybody okay with that? Salma, you okay with that one? Okay. Number 9. All right, I'm struggling with this today. All right, number 9. At what temperature and pressure do all 3 phases coexist? What's that the definition of? The triple point. So the temperature and pressure. So the pressure is 0.5 atms, and the temperature is 45 degrees Celsius. Okay? Now, from there, we're down to number 10. Is the density of the solid greater or less than the density of the liquid? All right, look at the solid. Generally speaking, I would take you to think about your solid and liquid. What do you know about a solid and liquid? Whose density is greater?
Solid.
The solid. When you look at it up here on the graph, which section is greater? The solid. There's a bigger section for the solid. So those two things should go together. Now, for number 11, would an increase in pressure cause the substance to freeze or melt? Look what's happening. As pressure goes up, what's happening to the solid? Get up here. What's happening to the solid section? Is the solid section increasing or is the solid section decreasing? The solid section is increasing. So if the solid section is increasing, that means it's doing what? It's freezing. Okay? Everybody okay with that? All right, now let me check over my notes. Because the last 2 days I have had to come in and show you what I have forgotten to do. So let me see if there's something that I have forgotten. See if we can avoid that for tomorrow. Yep, we did all that. We're good on that. What crystal structure does salt have? Okay, what? It is crystalline. It's not amorphous. Tell me this. What's its actual crystal shape? If I ask you that on the test. Which one's the hexagon? Who's the hexagon? Y'all are clearly not studying.
The crystalline is the hexagon.
Crystal. There were 3 that I gave you that were crystalline, and I told you had to know their shapes.
Ice.
Ice is the hexagon. Sugar and salt are what shape? Cubic. All right, we've done all that. We talked about that. We've done that. We've done that. Yep, we did all that. Came back and got that today. We did Le Chatelier. Done boiling. Yep, talked about that. We just did phase diagrams. We did all that. All right. I think we're good. I think we're on to kinetics without difficulty. Without Miss Wall forgetting to do half her lesson. Jeez Louise, I'm getting old. I'll be walking around with sticky notes on my chest next. All right. All right. Oops, I don't need this. Get rid of that. And pull up this again. No. I don't want this. The driving forces behind a reaction for the rest of the day, and pretty much, I would imagine, all of tomorrow. I would be surprised if we get it all done early in class tomorrow. Thinking about what we need to do, I don't think we'll get much further than that. Huh? No.
And the thing that says anything about it, I'm gonna be benchmarking with these kids. Crickets and all She comes in after what's going on. Me and her, she's like, oh, she's the benchmark. Who cares about the benchmark? And
Mhm.
can't be loud.
Mhm.
So don't let nobody say, don't do benchmarks.
Exactly. Besides that, out of 20 kids, I only got 9.
I see her kind of thin.
Kind of thin today. Exactly. Did you take notes yesterday?
Yes.
Thank you.
Did you talk to her?
I talked to Cross this morning, but I need to be able to send, and I didn't write anything down because it was just, chat about what happened. And she gave me a brief rundown, but apparently I need to send my people some stuff and ask for feedback. And so I thought if you gave me what you had, I could type up a little bit and say, send me your feedback, since apparently I need feedback on what they prefer. So, whenever you have time today, when you're not benchmarking for the things that are not important. All right. So, how do I want to start this? Do I want to start with collision theory or just go straight for kinetics? I know you want a chill day. I'm not interested in what you want.
We'll just get more practice on the others.
What other stuff?
The equal root where?
Nah. I don't have anything to practice on.
Why can't we do this tomorrow?
Because we could.
Yeah, and focus on equilibrium. Yeah, because I don't know how to.
Yeah.
My hand hurts, Miss Wall.
I've got one multiple choice sheet I can give you at the moment. We might be far enough to do the longer one. All right, for a successful collision, let me do the 5 rate factors and then I'll stop. I won't do the potential energy diagrams. I'll stop here. All right, basically we need 2 things, okay? Number 1. All right, and we're going to spend a lot of time talking about this with potential energy diagrams, and I won't go into that today. All right, a reaction must have enough energy. Okay, now tomorrow, since y'all want to practice, this is going to be called activation energy. And I won't talk about that today. Okay? But in order for any reaction to be successful, you have to have a minimum amount of energy. It's called activation energy. All right? When molecules, compounds, atoms, whatever happens to be reacting, hits each other, if they do not have enough energy, they literally slam into each other and bounce off, and they do not react. Believe it or not, out of millions of collisions, very few of them are successful. They literally bounce into each other and bounce off. Now, the second thing that they need is they have to have proper orientation. Now, the easiest way for me to explain proper orientation is like lining up 2 pieces of a puzzle, or have you ever gone to plug in something into an outlet and you've gone to plug the plug in and the plug won't go into the outlet? And you have to turn it over and plug it in the other direction. It's like one end is wider than the other end and you've plugged it in the opposite direction, you have to flip it over. Same concept. Molecules are oriented a certain way. If the orientation is not correct, when they slam into one another, they don't fit and they don't react. So they, again, just bounce off. They have to meet both requirements. If you don't meet both requirements, then you cannot have a successful collision. Okay? So in order to have a successful collision, do we want these molecules to only hit against one another once or twice?
Twice.
No, we want them to hit a whole bunch. Okay, so the whole idea behind kinetics, which we're getting ready to talk about, is we want to increase their chances of being successful by them hitting more often. The more chances they have to collide, the more chances they have to be successful. Does that make sense? Okay. So, everybody got what they need? All right. So, kinetics. Okay. Okay. Is the study of how fast a reaction occurs. So, some reactions occur really fast, some don't. We're going to talk about how we can make it go faster. Five factors affect the rate. We can make it go faster. We can make these collisions increase. How can we make more and more collisions to make the reaction go faster? How can we increase our number of collisions? Make successful collisions. How can we make them faster? What can we do to speed them up? Increase temperature. All right. If we increase temperature, the molecules move faster. They collide more often. More chances of successful collisions. Okay, that's what we're shooting for when we talk about successful collisions. All right, that's what all five of these rate factors are about. How can we get more collisions? If we increase the temperature, the molecules move faster. They collide more often. Anytime they collide more often, they have a better chance of being successful. So what else can we do besides increase their temperature? Huh? Not necessarily a smaller space. You're on the right track, I think. Two of them we talked about today. Talked about them in the opening. How can we change? For example, how can we make something evaporate faster? All right. Number two, increase the surface area. Okay. More exposed area. For the collisions. I thought I heard another answer back there.
Surface
What'd you say?
tension.
Not surface tension.
What do you say?
Concentration. All right, concentration is the number of particles, right? So if you increase the number of particles, there are going to be more collisions. Sort of like when you guys leave here and go out in the main hall at 1140, there's more people in the hallway. What's going to happen? You're going to bump into people. It's unavoidable. I only go to the bathroom, and 9 times out of 10, somebody bumps into me. I mean, I realize I'm large, but good God, people are not blind. All right. The fourth one, think biology class. How can we speed up a reaction and make it go faster? Think biology. Catalyst. Add a catalyst. That alone speeds up the reaction. That's its sole function. It doesn't participate. It doesn't do anything else. It just makes the reaction go faster. That's its only function. Now, number 5, I'm just going to tell you because you're never going to come up with it. You'll know it. You just won't know how to say it. Now, if I tell you nature of the reactants, can you think of something you've learned this semester that you can look at the periodic table and tell me, oh yeah, Ms. Well, that was going to react really fast. Give me something up there that you can say, that's going to react fast. Why? Cause.
I don't know.
Because it's in group 1.
Sure. All right. Group 1 is going to be fast. All right. Now give me someone who's slow.
Magnesium.
Who?
Magnesium.
Magnesium is not going to be too slow. That's in group 2. Give me somebody who's slow.
Helium?
Helium is pretty much non-existent. Give me somebody slow. Helium's not going to react at all.
Iron.
Oxygen's not too slow. Group 2 and 16 are the next fastest after group 1 and group 17.
Iron.
Iron. All right. Iron is going to be slow because it's where?
What's in the well,
It's in the D block. Okay. The D block are pretty stable elements. So they're going to be slower elements to react. Group 1 is going to be pretty fast to react. Now, helium, you could put helium is not going to react. Okay. Instead of putting slow, helium's not going to react at all. All right. That is really slow. Those kinds of things you know about reactions. Okay. So if you're trying to speed up a reaction, would you want to add something like helium? Good God, no. All right. But something like potassium that's explosive in water, that's certainly going to move it along a little bit. Okay. That's going to make it move faster. So when we talk about trying to get a reaction to move faster, to have energy and the correct orientation, and you want the two things to collide with each other, if you want more reactants to move faster, make them move faster by increasing the temperature. Increase their surface area. Think about it. Any of y'all ever add sugar to your tea or your coffee or anything? What dissolves faster, cubes or granulated? Granulated. That cube stuff, you got to stir forever to get it to dissolve. So increase the surface area. If you have more of it, it collides more. Yeah, I got to hold 9 people out of 20, Miss Fuller. Why do you think I got 9 Saturday school contracts in this class?
The time of the year.
It's killing me in an honors chemistry class.
What can I do about it?
Nothing, because I can't either.
Can't control the enrollment, can you? Put classes in.
Just be patient and kind if my failure rate's high.
I just be glad when this whole period is over. Laminar requirements is in the other period. You all are not tested or anything today.
We
Come
were
on.
supposed to be. Don't tell anybody.
In another subject. So,
Okay.
Okay. All right. He'll be very late or I'll send you an email.
Okay. Tell him he's tested in my class tomorrow, though, so come by and get his stuff he's missing.
I will.
Okay. All right. Questions? All right. So Betsy Bay does not want me to do potential energy diagrams. She wants to practice some of the stuff we've been doing. All right. So let me see if we've done enough on my multiple choice. Let me flip through it real quick. I think we have. All right. Yep. The only thing, we haven't done 22. I can tell you what that word means. Yep, we can. We can do all that. All right, so that's available practice. Let's see if we can do some practice. All right, one for you, two for you, you got one for Brian. I gotta tell you one word, and I'll tell you what that one word is. Brian's gonna stay off that phone, I'm gonna put it on my desk every day you come in.
I was listening. She said,
All right,
okay.
everybody have one? All right, the one word I have to tell you is a word we're gonna do later in the week, but you can use this word anytime. Look at question 22. Find the word in 22. It says the entropy of solids. Write the word disorder over the word entropy. All right, if you change the word entropy to disorder, you read the question as the disorder of solids, you'll be fine. All right, find question 22. Okay, find question 22. Change the word entropy to disorder. And you can still answer the question because it's just asking you about the order of solids. Change the word entropy to disorder. That's what it means. And we're going to talk about that word later in the week. Okay? But the rest of the questions, we've done all of those.
Hey, Ms. Wall.
Yeah.
In 8th grade, my science teacher, he told me that, this is why I want to say potassium. He said that potassium was submerged in water because it's really reactive, and if it touches something about
It has to be
oxygen-
submerged in like mineral oil or kerosene. It can't be submerged in water.
And oil, I meant.
Yes.
And he said that if it like touched oxygen, it would like explode or something.
If it touches water, it will explode. Yes. And there's, like today, there's water vapor in the air. So yes, it would explode.
That's cool.
Anybody have a question? That's about it. You working?
The escape of